Hi, it's me again. Good morning. Yes, we'll video again. Hopefully this time would be quick and you'll get used to it as well. As you can see, the topic today, the topic there is 2018 Chemistry 12 Clip 002, and hopefully you enjoy your Clip 001. And yeah, I'm not sure you have any questions. I heard people saying that they couldn't get the Dropbox account. If you don't have the Dropbox account, send me the email. I'll send you the link. As long as you have your browser, you should be able to to view all the information you need. So you don't really need a Dropbox account to get anything. So there's no excuse if you I don't have Dropbox, so I'll wait for me to come back. Don't do it. As long if you still have problem, go to the office. I have sent all my file to the office. Probably the first day of the week or second day of the week. Then you can go in there, ask them, see whether I have left any work for you guys. So don't try to say if I don't have Dropbox, I will wait until I come back. You don't have time to do that. As a Year 12 classes, there's no time for you to lose. So let's go straight into teaching today. I don't really so remember what we do yesterday, not yesterday but last video. We generally talk about something called thermodynamic chemistry. So if I ask you what is thermodynamic chemistry, I hope that you were able to tell me that thermo means heat, dynamic means moving. So you were able to see there's heat moving into the system and outside the system. So whenever I need to explain thermodynamic chemistry, there's always the term that I will use, which is called system. System means very simple stuff. All the chemicals involved in the reactions, whether it's reactants or whether it's product, in generally we group them together as a system, which is all the chemicals, all the matters that you can find inside a reactions. For a simple system, I always use the simplest gases you can get. Hydrogen gas. When hydrogen gas burn with oxygen combust. When they combust, it generally form a wonderful chemical water. By just looking at the reaction, it's not balanced. So if you need to balance the reactions, put the 2 in front of the hydrogen and then you put the 2 in front of water. Hopefully you know that when you write the chemical reaction, you will need to have the gases at the state attached on each of the molecules. So here is the reactions and the whole reaction with the left hand side here. So make sure that I have to say that that's the left hand side before the arrows, and that is the right hand side after the arrows. So the left hand side and right hand side is very important in terms of dynamic thermodynamic reactions chemistry. You need to stay most of the time on the left hand side. We call them a reactant if there's more than one reactants. And then we have the right hand side, which is our product, not R, P. So we've got our products here on the right hand side. Left hand side, right hand side, reactants, product. So I will not explain this again. Make sure that when I say system means the whole thing. Reactants and product equals to system. They can move forward or they can go backward. Later on in the course, you'll find a very interesting concept. Reactions not just going forward, it could go backward sometimes, not sometimes, all the time. Then when you try to understand what is the system, then there's another term that I will use a lot, is called surrounding. Lots of people use different terms. I like to use surrounding, system surrounding. Both of start with S is easier for me to remember. And the surrounding means where the heat goes. So it would be either the heat leaving the systems go into the surrounding, or the heat or the energies come from the surrounding go into the system. So for thermodynamic chemistry, we need to know about the term system and the terms surrounding, and the things in between that they will swap things in between them. The only thing the thing that we focus on here is the energies. Most of the time we use heat to explain those energies moving into or leaving from the system. Just exchange. There's an energy exchange or swap between system and surrounding. So still remember one thing called thermodynamic equations. If I write this equation again, so which is here hydrogen gas with oxygen gas going into water. Put a 2 there, put a 2 there, then the gases as a state. So now we've got a complete chemical equation. This is only chemical equations. Lots of time in this course, it asks you to write some other thing called thermodynamic equations. Thermodynamic chemical equations, not just the equation, we have to add one more information at the end, which is called delta H, and that delta H means heat change. If you can't remember what delta H means, go back to the last video. Then I have explained it to you, and you will find that delta H means the energies changing in between the system and the surrounding. And this time, for this particular reaction, is a negative sign, and it's 484 kg mol minus 1 per mole. So that is a complete thermodynamic equations, and the negative basically means release. So there would be a 484 kilojoule energies released if you react hydrogen gas with oxygen gas. So when you try to look at that, there's one more information we have to focus on, which is the number. What does 2 means? And there's a 1 here, there's another 2 there. If you consider this is a delta H and there's an energy release, the next question you will ask yourself is, how much hydrogen gas do I need to release or let go those 484 kilojoules? And we have to look at the number 2 there. 2 means 2 mole. If you take 2 mole of hydrogen gas, 1 mole, 2 mole, then you react with 1 mole of hydrogen gas. How many mole of gases altogether? 3. 2 hydrogen gases and 1 mole of oxygen gas. 3 moles gases react together. When they react together, it forms, interesting, only 2 moles of water. How come there's a 2 mole of, 3 moles of gases make 2 moles of water? Then you should be able to tell me very, very soon, because of water molecule is bigger. When you have 2 or 3 moles of gases, they're all smaller molecules, then you make 2 moles of bigger molecules. And that's not hard to understand. So we're not doing math here. 2 plus 1 is not equals to 2. We have to notice there's some molecules are smaller, some molecules are bigger when we try to look at the mole ratios. So delta H is equals to negative 484 kilojoules per mole from these reactions. If you take 2 mole of hydrogen gas, react with 1 mole of oxygen gas, it produces 484. Then very quickly, if I give you a little mass, 2 mole of hydrogen gas going to react, it releases 484 kilojoules. How about if I have a quarter of hydrogen gas? So very quickly, from 2 mole down to a quarter is 8 times smaller. So you can tell me straight away if you use the calculator. The calculator there, give me a second. So now if we have this, basically you can tell 484. 484 divided by 8 would equals to 60.5 kilojoules. 60.5 kg would be released if we try to react. If we try to react those hydrogen gas together. Then you will also ask yourself a question: if 2 mole hydrogen gas is going to react 1 mole of oxygen gas, how much oxygen gas do we need to produce -6 or to release 60.5 kilojoules? So is 1/8 of 2 mole, then 1/8 of that divided by 8 would be 1/8. 1/8 is 0.125 mole. So a quarter, 0.25 mole of hydrogen gas react with 0.125 mole of oxygen gas would produce -60.5 kilojoules. Right? So for this, that would be a very, very useful information if a question giving you a delta H, because you can simply try to convert your materials or your reactants or even a product in terms of the amount. You find out the amount of it, then you use the appropriate ratio. You can find out how much energy is being released or being absorbed. Now, let's have a look at these reactions. So if I'm giving you the same reaction, but this time, instead of putting a 2 in front of it, I put a half in front of the oxygen, then I will have 1 water down there. So is it possible for us to write this type of chemical reactions? Yes. You're allowed to put fraction as a coefficient, so that's full stop. Just allowed it. You can put 0.1, 0.2, whatever you want, because the coefficient there just means the ratio. The ratio can be 1 to 100 or 1 to 101. There's no restriction for the coefficient. However, when you try to look at hydrogen and oxygen gas, then one thing that you need to change is the delta H would not be exactly the same, because compared with the one above, we use 2 mole of hydrogen gas, 2 mole there. Now we only have 1 mole. So therefore, the delta H would be half of it. It's -242 kg per mole. So if that's this, hope everything would be understand. So now if you have changed one of them here from 2 into 1, then you can halve the delta H. How about I do it like random? 3H2 going to react with 1.5 O2 turning into 3 water. So then I have another. It doesn't really look good, but if I just make it up, try to make this into that so very ugly numbers, I would say 3 and 1.5 and then 3. So what we do next is we have to change this into 3 times more. So 3 times that equals to let's say 3 times 2 is 6, 3 times 4 is 12, 1 is 726 kilojoules per mole released. Right? So then the thermodynamic need to be balanced on both sides, the front here and the back. As long when you change the number of the coefficients, then you need to change the number for the delta H, right? So that's simple mathematics that you need to bear in mind when you try to look at thermodynamic equations. So what I'll do next is try to go back to this graph. Still remember what we call what do we call the energy profile. So what is the energy profile for a exothermic reactions? Exothermic reaction energy profile can be drawn like this. So you start exothermic is energy release, you always start your chemicals at the top, then you end up your chemicals down below. The reaction coming from the top all the way down, then stop. So if that is, or we call this energy profile because the y-axis is referred to the energy content, while the x1 would be the time. The first line there is the start of the reactions, and the line at the end is the end of the reactions. So at the beginning of the reactions, let's say I'll try to write A react with B. It turns into D. Let's say try to write the equation next to it. 3A plus B turn into 2D. So we have 2 here and 3 there. So 3A with B it turned into 2D as this particular exothermic reaction. And energy profile would be is a graph, right, with x and y axis. Then 3A plus B forming 2D. What can I do more? Is what happens if I say this is from 30 and this is 40, 50, 60, 70? So from 30 to 70 there. Then I'll ask you one thing is what would be the delta H by looking at the graph. You should be able to tell me delta H is equals to the product of the energy coefficient, energy content, minus the reactants. So what would be the product? The product is down here, 30 kilojoules. Take away the one at the top, which is 70 kilojoules content, energy content holding into it. When it's exothermic reactions, A and B hold more energies, chemical energies, potential energies inside them. That means that it's generally, you can assume that it's a more complex molecules. It's more complex, it turns into a bit more simple. When a complex molecule turns into a simple molecules, 30 kilojoules take away 70, you will have negative 40 kilojoules at the end. Delta H equals to negative 40, straight away, right? Makes sense. If it makes sense, then how about I change the whole thing opposite? Now I do endothermic. If I flip the reactions like this, 2D can react and turn it into 3A and 1B. If I flip the whole thing, then you should be able to tell me one straight away, this is a endothermic reactions. Endothermic reactions. As you know that the energy content for 2D, which is 70 at the top, and the energy content for 3A plus B is, the other way around. The energy content for 2D is down there, 40. That's 2D, 40, 50, 60, 70. So that's 40, 50, 60, 70, 70 there. 70 at the top, which is your A and B, as A and B is more complex. Sorry, my mind's not running properly just then. Then the whole reaction move up. So if I asked you to write down the delta H, the same equation applied, I will use the product. But this time the product is on the right hand side, which is 70 kilojoules, take away 40 kilojoules. And what would be the delta H? The delta H would be a positive number, 30 kilojoules. Right? Compare with the one that above. Oh, sorry. I start with 30. Change a little bit here. I can fix it up. That's 30. That's 70. Then still changing this one. That's not 40 anymore. That is 30, and the one that would be 40 kilojoules. But this 40 kilojoules is positive instead of negative. So you may ask me like, oh, why do you need to learn all this? How about if I make it up a bit worse? Let's say I give you 3A plus B forming 2D is delta H equals to negative, let's say negative 100, which is a bit easier. Negative 100 kilojoules per mole. One thing that I need to mention is the per mole means we use mole to measure it. Doesn't mean that everything is 1 mole, right? Mole is just the unit that we use. It just refers to the unit, not 1 mole. Only thing that you see that refer to 1 mole is the coefficient has 1 there. When the coefficient is 3, it means 3 mole, right? Now, if that's the case, what if I do this to you? I make it to 4D, going into 6A and 2B. Would you be able to do what is the delta H? What is the delta H? The delta H would be, you can do at least 2 things, because when you go forward, so when you go like 3A into B, you need to do a flip first. So let's do a flip. When you do a flip, means that you take 2D turning into 3A plus B. So when you do a flip, from a negative, you becomes a positive kg per mole, right? Then if you try to do 2 into 4, 3 into 6 and 1 into 2 from 100, you have to double. When you double your values from 100, it becomes 200 kg per mole. Answer done. So very quickly, by giving you one equation, you can do all these calculations and flip them around, double them, then you find out the delta H yourself, right? Is it all good? So if that's all good, then I'd like you to do one last thing before I move on into the new topics. The one last thing is I'd like to give you 5 grams of hydrogen gas. I need you to find out what will be, just put a question mark there, and then what would be the delta H in terms of kilojoules when it combusts. So when it's burning with oxygen gas. So you can see someone's banging above me. In Hong Kong is apartment, and we all close to each other. Wherever people doing upstairs, you definitely hear it. However, if you're someone outside yelling at the kids, you're definitely able to hear it. Yeah, some guys up there doing all the banging, so I don't know what to do. Now, give yourself a chance to think about this question. We have 5 grams of hydrogen gas, and you need to use equation to begin with. So please think about what would be the equation that you use: a hydrogen gas with the oxygen gas, and what is the product? I can hear that. Hopefully you say this is water. So hydrogen react with oxygen turning into water. Then you're probably able to go back to look at your equation above. The delta H there is equals to negative 404 kilojoules mole as the unit. Then we have to balance equation. Put a 2 there, put a 2 there. Try to put the state next to it as well. Then here we've got every information we need. Then go back to look at 5 grams. Remember one thing that we do, 2 mole produce negative 404 kilojoules. Then as long as you ask yourself how many mole of hydrogen in 5 grams of gas, you should be able to tell the answer. What is the number of mole of hydrogen gas here? Is equals to mass over molar mass. We've got 5 grams. Molar mass of hydrogen is 2 grams. So there is 2.5 mole. If 1.5 mole, if 2 mole there, give you is 484 kilojoules from 2 mole of hydrogen gas. Then how much energy is the X, as is your answer, from 2.5 mole. This is the very basic equation you can do. Rearrange it, blah blah blah. X is equals to 484 divided by 2 times by 2.5, which is, I don't know the answer. So let's say 404 divided by 2 is 242 times by 2.5, which is 605. That's the answer. So let's say 605 kg being released. So sometimes people are very tempted to write negative straight away. Don't write that as a negative, because my question is not asking you to give me delta H. My question is asking you to find out how much energy released. So you would just write me a simple sentence. It's 605 kilojoule released from burning 5 grams of hydrogen gas. And that is your whole answer. Right? So that means that you have understand, or you've learned today, that how do you able to do exothermic and endothermic calculations. So it's close to half an hour video. I know that is more than enough for just watching me in the video writing things. So now I need you to start work on your what do you call? I give you a 10 question guided question every single class. So you please use the rest of the time. So hopefully you set yourself about an hour today, and you will start doing your 10 guided questions. And make sure that you send this question by Friday. Okay, and this is the, let's say, is a week 2. So I expect that you come back from the camp, and the first thing you do would be this one, and you have time to do it. So that means when you come back next Friday, just today, the one that the time that I'm doing is 31st of January. Then I expect you finish your camp on this tomorrow. So the first, the second. So probably over the week, and maybe by Sunday this time. Try your best to do it. Or the latest has to be next Friday. Next Friday would be the 9th. Okay, so the latest, the 9th of Feb, would be the one that you try to finish those. You will have more. So I'm giving you at least another 2 videos in week 2. So 3 videos, 30 guided questions, then and the homework as well. Right? So hopefully everything worked out for you, and good luck with the question. Thank you. Bye bye.